Good afternoon. Welcome, everyone, to this talk. You've heard and seen the title. The talk's a little bit more specific about some general problem, and it consists essentially of 4 parts. In the first part, I will introduce you to the concept of higher-order patterns or higher-order correlations for those of you who are not familiar with it, briefly, and then show you 2 examples, real-world examples, to give some motivation for the problem, why we're talking about it, dealing with it, why it's interesting and important to do this kind of analysis. Thirdly, I will try to explain to you the core problems in detecting and validating these sorts of patterns, which is a little bit counterintuitive, but I will show you. And finally, I will show you a working solution, a new one, that I hope that will be useful in the future. So, first, what is a higher order pattern? What do I mean by a higher order pattern? You can see this here. You can see my mouse, right? Yes. So we have here, let's say, a data set that has, in this case, 5 dimensions. One dimension is the x-axis. That can be anything. It can be time, and you can see some events here demarked, or it can be any other feature, any other class. And then you have here these 4 parallel trains, time series, whatever you might call it, 4 different qualities, features. And so this is a very general sketch of the whole thing. So you can think almost any data you can cast into this sketch. So you have n dimensions, x and y, and any number of traces, and you're looking for patterns of higher order, meaning correlations that go beyond pairwise correlations. So computing pairwise correlations is in a way very simple and straightforward. Everyone knows that. The problem becomes bigger when you're searching for correlations that go beyond this pairwise thing. So this is depicted here on the right. If you observe in your data, in this case, this 4-piece pattern, you don't know just by observing if it's happening randomly just by some chance, some coincidence, or if there is a real underlying, as is shown here, a real underlying correlation between all these 4 elements. So you can see the definition here. An observed correlation between items or events is called genuine if it cannot be explained by correlations of lower order, i.e. meaning by a random superposition of any of its constituent parts. So this is what the talk is about. This is the whole problem. This is what we are after. Why is it interesting? Well, if you would know that one of these patterns that you observed is a real higher order pattern, you know something about the dependencies in your data. So these traces, number 1 to 4, can be dependent, conditioning on something. And this is the first thing you get out of this result. If you have a real higher order pattern, you know there are some dependencies. Also, once you have these patterns, those that are really genuine higher order patterns and that are significant, you also know something about your data in terms of fingerprints. So you know what are the features in your data that might carry a meaning or definitely have a meaning. And third, once you have these fingerprints and you characterize them, and you see, okay, how do they actually look like? You might deduce something about the hidden causes of these patterns. And this might even lead you to a model of your data. So, for example, if you have very high-dimensional data and you figure out that the only correlations you find are of order 2 and 3, this has a meaning. It's, of course, a completely different story as if you had a correlation of order 100 or something like that. So this has consequences for your model of your data. Okay, why might be interesting? Let me show you 2 examples. First is parallel time series. I took here, just randomly, has no further meaning, these 4 stocks, IBM, Google, Hewlett-Packard, SAP, from the last 10 years. So this is the price per share in US dollar that you see here. By the way, within Mathematica, you can always access from the Wolfram server these data. It's called financial data. You have roughly 90,000 different stocks here in the database. I choose these 4, and you can see the development from the last 10 years here in this sketch. So why would it be interesting to look for higher order correlations? Well, first question, are these time series independent? No, actually we know they are not, simply by the fact that the same people are buying and selling these stocks. So what would be an interesting question? Well, I would be interested in saying, well, do they somehow behave in a consistent way so that I can make predictions for one, looking at the others back in time, something like that. Yeah, I could do that. I could transform the data, employ a little function, and this is the same data here. And these are the days, so this is 10 years, right? And these are simply the days with a 2% or more than 2% increase in stock price compared to the day before from these stocks. So we can now, in principle, run an analysis on this data set here and look if there are some dependencies between these. I mean, it has no meaning that it's only that it's these four. You can think of 100 or 200 more or whatever you like. Also, I would like to motivate you to look at your data in different ways. So if you have time series like this, you can always transform this in some way, like here, and have a different look at it. Okay, second example, completely different example. Genetic variance in health and disease. In general, the story goes like this. We have here 1,000 healthy people, 1,000 patients, and on the x-axis is the whole genome, so the whole sequence of single nucleotide pairs, SNPs. And you can run an analysis for each of these positions. So on the x-axis is the position, and you can run an analysis with some statistical tests. This is pretty much straightforward. And come up with some positions, like here in this case, where the cohort of patients differs significantly from the cohort of the healthy people. And then you have a result. You say, okay, well, here we have some significant difference on average between the patients and the healthy people. This is how this sort of research is done nowadays. Okay, where does this lead to? So, example from schizophrenia research. Here's one sketch. Here's one part of the DNA on the x-axis. So the x-axis means position of single nucleotide pairs. And what you get out of this sort of analysis is these positions that have a significant p-value or some high correlation coefficient compared to the healthy cohort. And then you see, okay, wow, there's some really significant positions here. By the way, this is some area. Here you see some gene, some region for some gene. This is an area, a non-coding area. If you scan the whole genome for these sorts of things, you get these sorts of results. So what does it mean now? Where are the problems? The point is, if you have one person and you see that, okay, it has this one gene variant here or there, the susceptibility to have this, in this case, schizophrenia or other diseases, is extremely low. Taken all together, these findings that we know by now from this sort of research explains about 5% of the incidences of the diseases. So this means that, of course, one such SNP, one such variant doesn't explain close to nothing. So we're missing an awful lot. Why? Well, of course, because the effects that are leading to the disease are additive. So meaning we need to look at higher order patterns. We need more than one factor to know with a certain precision that the disease is there. So meaning we need more than one factor, not only from the genes. We would also like to do this from a blood sample, liquid biopsy. We would not only scan the genome, we would like to scan the transcriptome, which is the RNA level, or we would like to scan the proteome, so we can have a data set, and this doesn't take more than a day nowadays for one person to have these data that is extremely high dimensional. And we need to search for these high order patterns in there, and nobody's done that yet because it simply hasn't been possible. Yeah, so I hope by now you got an idea of the complexity of the whole thing. So it's very easy to have data sets with a dimension of 1,000 or more. And we need to analyze the additive effects, we need to analyze the higher order correlations in these data. So, of course, another example of market research, you can do the same thing for market basket analysis, visited websites, you name it, whatever you like. It's always the same, just to mention it. So what is the task? So this is a general sketch here. So we have these parallel whatever traces. Then we have some dimension on the x-axis. In this case, by the way, this is real data from neurons. So these are neuronal signals here. And x-axis was time, but this doesn't play any role now here for the concept. Can be anything. What's depicted here in gray is essentially one data point. So the region that's denoted by W is one data point. So we have, from each of these dimensions, we have some quality, either some event in time or some class. So the class could be defined further by this window tau. So this is the general sketch. So what would we need to do in order to analyze the correlations between all these dimensions here? Well, we need to look for repeating patterns in the data and to compute their significance. And then we would have it. So where's the problem now? Of course, this very simple brute force approach is very intuitive and could be done in principle, but where's the problem? Well, the problem is the following. The combinatorial explosion of the number of candidate patterns in tests with increasing number of dimensions. So if we have only 4 or 5, it's completely doable, there's no problem. If we have 20, so like 20 dimensions here, which can, I mean, it's not a lot, it can easily be reached. The number of combinations of all these 20 dimensions within one data point, one window, is precisely 2 to the power of, in this case, 20 minus 20 minus 1. 20 for the minus n for the single dimension patterns and minus 1 for the empty set. And this is the number that you see here. It's a little bit more than 1 million. But this is only one data point. So if you have really 20 events, 20 classes in this data point from your 20 dimensions, you need to do more than 1 million tests. This gets worse if you get bigger. Let's say 100. We can easily think of 100. I mean, this is already a very large number. It's only one data point, and the number of tests required. If we go to 1,000, look at that. It's a ridiculous number. It's like the number of atoms in the universe, something like that. So the brute force approach would be very simple, but it simply doesn't work. It will not work. Nobody did that because even a supercomputer would need hundreds and thousands of years to compute that. Whew. So what can we do about it? Of course, it's research in progress. Has been a nagging problem for decades, actually, and I only cite a few here. These references here deal with detecting temporal patterns in parallel time series, but in principle it's all the same. It doesn't need to be time series, can be any sort of data. So there exist methods for the more or less exhaustive search with different statistical testing. For these parallel time series, the common problem is that there is no test for genuine higher order correlations. So you find maybe a complex pattern and that's repeats significantly often, but there's no real test for genuine higher order correlations in these methods here because of the problem of the combinatorial explosion. There are a few other works dealing with it in other ways. So they are not taking this brute force approach, but they are using analytic models for that. But they don't get around the core problem. Still, if they come up with a model and the data have more than 10 dimensions, so you need more than 10 variables in your model, you suffer from the same combinatorial explosion. So what can we do about it? Well, I'm going to show you now a working solution. I'm going to demonstrate this right here in a minute and show you the results. So this is the statistical design. The magic appears here. I'm not showing you now all the details of this. For several reasons, but this is the idea of the whole thing. We detect repeating higher order patterns in the original data. Now we need a random model, so we need to know, okay, if I observe a certain pattern, is this random or not? How can we answer this? Well, by constructing surrogate data from the original data. So we sample from the empirical distribution, so we do not need any parametric model, any analytic model for that. We sample from the original distribution, and destroy exactly those features in the original data that we are looking at, that we try to analyze. Exactly those and nothing else. This is the trick, and this is the difficulty with it. So this is a scientific problem in itself. Here are only 3 examples. How you do this best depends a lot on your question, on your data. So if you have these parallel time series, you could, and you look in certain time windows. So on the x-axis, on certain time windows and patterns in this time window, you could try to jitter randomly the timing of the events in your data, either the whole train or individually, or you swap some intervals. And in that way destroying the temporal structure across your dimensions exactly on the time scale that you're analyzing, not on a larger time scale. So you leave intact the number of the events, the rate of events, the rate covariation of events, the distribution of inter-event intervals, everything like that. That's the idea. And then you do the same analysis with each of the surrogate data sets. So you construct more than one, like 20 or 100 or 1,000, how many you need for your statistical test, and do the same thing. And then you do the first level statistic here. You do a statistical test for each pattern that you found in your data compared to the surrogate data. So meaning, if this one pattern in your original data occurs significantly more often in your original data than in the surrogate data, you say, okay, it's significant, all the others are dropped. This you do also with all the surrogate data sets. So now you see it already, it's not only a combinatorial explosion with the patterns themselves, but also you need a number of surrogate data sets, you need to repeat the whole thing, you need to do the same thing for all the thousands of patterns you might find that repeat in the surrogate data, in the random model. Do the same thing. You will also find, just by chance, significant patterns in the surrogate data, for sure. So you need this second level statistical test, this one, that compares the overall number of significant patterns that you found in the surrogate data compared to the original data. If the original data altogether passes this test, then you can say, okay, well, I have some significant results. Okay. Now I will show you real-time computation. This is the simulated data I feed in. I simulated this from gamma processes lasting for about 50 seconds or something. I have these 30 parallel traces, and I inserted these patterns consisting of 5 units each, 6 of these patterns, every second, but they overlap with all the other events in the data. So the task is to detect only these 6 patterns here, and no other patterns. And I will start the computation now. So this is the notebook. I will now simply initialize the values. Then I will load the data, do the analysis. Okay, what do you think? How much time would it take to do one run? So to detect the patterns in the original data, the repeating patterns, and only those that are real higher order patterns. Well, I have a notebook here. It's about 20,000 events in the data, 30 dimensions. And it's done now. So it's not a lot of time. And now we will do the same thing with the surrogate data sets. In the beginning, I told him to construct 20 surrogate data sets. So this means, you will see this in a second, we will now have to wait about 3 minutes. Then I will show you the result. And in the meantime, I'm ready to answer any questions you might have.